Hello, this is a talklet that will introduce the basic concepts and vocabulary that are relevant to heat integration, and we're going to introduce these concepts by considering heat recovery between just two streams, one hot stream and one cold stream. So, imagine that we have two streams. We're going to plot them on these graphs. So we have a hot stream that needs to be cooled from 240 degrees down to 40 degrees, and it's going to lose 800 kilowatts of stream enthalpy in the process. So here it is, we've plotted it on our graph. It starts at 240 degrees Celsius, loses 800 kilowatts of heat, and ends up at 40 degrees Celsius. And meanwhile, we also have a cold stream. This one is initially at 80 degrees C. We want to heat it up to 205 degrees C. To do that, we're going to have to supply 1,000 kilowatts of heat. And so let's plot that on our graph. There it is, starting at 80 degrees, ending up at 205, and picking up 1,000 kilowatts of heat in the process. Now, let's remind ourselves that the flowing heat capacity, which has the nomenclature Cp, is defined as the product of the mass flow rate and the specific heat capacity. Because it's the product of these two things, the mass flow rate and the specific heat capacity, that determine how much of a temperature rise you get for a given amount of heat input. If you had a larger mass flow rate for a given amount of heat input, you're trying to heat more material, the temperature rise that you get isn't going to be so great. Similarly, if it has a larger specific heat capacity, that means it's able to hold a lot of heat without changing its temperature much. So a larger specific heat capacity would also have the effect of giving a smaller temperature rise for a given amount of heat input. Therefore, the relationships between the flowing heat capacity, the heat input, and the temperature rise are shown in these equations. Delta H equals Cp times delta T, so the change in enthalpy is equal to the flowing heat capacity times the change in temperature. The flowing heat capacity is therefore the slope of the graph of delta H versus delta T. So the slope of that graph would be given by delta H divided by delta T. Now our graph is the other way around. We've got temperature on our y-axis, heat flow on our x-axis, and so the slope of our lines is 1 over Cp. So clearly for our particular hot stream, it has a flowing heat capacity that can be calculated as 800, which is the heat flow change, the stream enthalpy change, divided by the temperature change, 240 minus 40, which is 200. 800 over 200 gives us 4 kilowatts per Kelvin. And there it is, 4 kilowatts per Kelvin for our hot stream. The flowing heat capacity of our cold stream, it picks up 1,000 kilowatts of heat. That corresponds to a temperature change of 205 minus 80, which is 125 kelvins, and so its flowing heat capacity is 8 kilowatts per Kelvin, and there it is. And we remind ourselves that the larger the flowing heat capacity, the smaller the slope of the line on a temperature enthalpy diagram, because a larger flowing heat capacity means a smaller temperature change for a given amount of heat input. So there's our two streams, our hot stream that needs cooling, our cold stream that needs heating. Now we could cool the hot stream with, for the sake of example, cooling water at 20 degrees. Let's imagine our cooling water comes in at 20 degrees and we're going to set it up so that it comes out at 60 degrees Celsius. Now the size of the heat exchanger that we would need depends on the size of the temperature driving force causing heat transfer to occur. If we assume a pure countercurrent heat exchanger, then the temperature driving force is given by the log mean temperature difference, and that's described by this equation. Delta T log mean equals the temperature difference at the hot end of the heat exchanger minus the temperature difference at the cold end of the heat exchanger divided by the log of the ratio of these two things. So in our particular heat exchanger, at the hot end, the temperature difference is 240 minus 60, which is 180 degrees C, at the cold end of the heat exchanger, our hot stream is coming out at 40, our cold stream is going in at 20. The temperature difference between these two is 20 degrees C. So, putting these numbers into our equation for the log mean temperature difference, we end up with a log mean temperature difference of 72.82 degrees C. Now, the size of the heat exchanger can then be calculated from the equation Q equals UA delta T. We know our delta T. Let's assume, for simplicity, for the sake of illustration, that the overall heat transfer coefficient is 1 kilowatt per meter squared Kelvin. Then we can calculate the required area for our countercurrent heat exchanger as A equals Q over U, delta T log mean equals 800 over 1 times 72.82, which comes out to be 10.99 meters squared, which is obviously much too precise. We'd say 11 meters squared. For the sake of illustrating the calculations, we're reporting these a bit too precisely. So, 10.99 meters squared is the size of the heat exchanger that we would need to cool down our hot stream using cooling water. Similarly, for the cold stream. For the cold stream, we're most likely to heat this up using steam. Steam condensing, for example, at 240 degrees C. So we can put that in there. Our steam condenses, gives up its latent heat of condensation. In so doing, it doesn't change its temperature. So the temperature stays at 240 degrees C, but we're providing enough steam to provide 1,000 kilowatts of heat, which will heat up our cold stream from 80 up to 205 degrees C. So we could do this. Again, at the hot end, the temperature difference is 35 degrees C, 240 minus 205. At the cold end of our heat exchanger, the temperature difference is 240 minus 80, which is 160 degrees C. Putting these into our equation for the log mean temperature difference, we end up with an average temperature driving force of 82.25 degrees C. And again, this would give us an area of a heat exchanger, assuming pure countercurrent flow, assuming a overall heat transfer coefficient of 1 kilowatt per meter squared Kelvin. We would end up with an area of 12.16 meters squared for this heat exchanger. So, overall, we have undertaken 1,800 kilowatts of heat transfer. We've got one heat exchanger with 800 kilowatts of heat transfer in order to cool down our hot stream. We've got a second heat exchanger with 1,000 kilowatts of heat transfer going on in order to heat up our cold stream. And these two heat exchangers have between them a total area of 23.15 meters squared. So that's our base situation. But we could consider attempting some heat recovery. To facilitate this, let's plot our two lines on the same graph. So there we are, we put them on the same graph. Now we're only concerned about enthalpy changes. It doesn't matter where the enthalpy starts and finishes, it's only enthalpy changes that matter. So we can plot our curves wherever we like on the enthalpy scale. We can move them horizontally to start and finish wherever we like. So here's the situation then, with no heat recovery, total of 1,800 kilowatts of heat exchange. We'll move our cold stream along so that it doesn't overlap at all with the hot stream, and between the two they're showing 1,800 kilowatts of heat exchange. So that's the situation with no heat recovery. Now, clearly, we can't cool a hot stream all the way down to 40 degrees Celsius using a cold stream that's initially at 80 degrees Celsius. That just can't be done. Similarly, we can't supply 1,000 kilowatts of heat to the cold stream using a hot stream that only has 800 kilowatts of heat to give. So clearly, we can't supply all of what these two streams need from each other in this way. But we could do some of it. We could cool our hot stream down some of the way. For example, we could cool it down to 140 degrees. There it is, 140 degrees. So we would have a heat exchanger that our hot stream enters at 240 degrees, comes out at 140 degrees. Our cold stream would be entering this heat exchanger at 80 degrees. sorry, going back a moment, our hot stream in cooling from 240 to 140 degrees. We remember the flowing heat capacity of our hot stream was 4 kilowatts per Kelvin. So 4 times 100, our temperature drop here is 100 degrees. So 4 times 100 is 400. So we're giving up 400 kilowatts from the hot stream. We're losing 400 kilowatts from the hot stream. Our cold stream enters the heat exchanger at a temperature of 80 degrees. So let's move that so that it corresponds to where the hot stream exits. Our cold stream enters at 80 degrees. It picks up 400 kilowatts. We remember its flowing heat capacity was 8. So 400 divided by 8 is 50. So our cold stream is going to heat up by 50 degrees. It started out at 80, 80 add 50 is 130 degrees, there it is. So our cold stream is going to come out of this heat exchanger at 130 degrees, having picked up 400 kilowatts of heat. Now the rest of the cooling of the hot stream down to 40 degrees, we'll need to use cooling water for that. We've still got 400 kilowatts of heat that need to be removed from our hot stream. And again, we're going to use our cooling water entering at 20 and coming out at 60 degrees C, and that will take away the remaining 400 kilowatts. We remember at the start, we said our hot stream had to lose 800 kilowatts. Okay, we've now lost 400 of that into the cold stream, and we're losing the remaining 400 using cooling water. Similarly, our hot stream, we said at the start it needed 1,000 kilowatts of heat altogether. We've now provided 400 of that from our hot stream. The remaining 600 we'll continue to provide using hot utility, using condensing steam, and that's going to be 600 kilowatts of condensing steam. So we now have 3 heat exchangers, and we've divided our graph up here into 3 intervals. So we've got, going from the left to the right, we have a heat exchanger that uses cooling water to bring our hot stream down to its final target temperature. And there's 400 kilowatts of heat transfer going on in that heat exchanger. There's our heat recovery heat exchanger, also transferring 400 kilowatts of heat between the hot and the cold streams. And there's a final heat exchanger that brings our cold stream up to its target temperature of 205 degrees, using steam condensing at 240 degrees. Once again, we can calculate the area for each of these heat exchangers. So considering the first one, it's log mean temperature difference. You can work it out offline if you wish, but it has a temperature difference of 80 degrees at the hot end and 20 degrees at the cold end, giving a log mean temperature difference of 43.28 degrees C. Our middle heat exchanger, its log mean temperature difference is 82.49 degrees C. And our final heat exchanger has a log mean temperature difference of 65.49 degrees C. We can now calculate the areas for each of these heat exchangers, giving us the total area by adding up the areas for each of them individually. So the area for the first one is given by 400, which is its heat transfer duty, divided by 1 times 43.28, which is its log mean temperature difference. Similarly, for the second one, 400 kilowatts of heat transfer. The third one has 600 kilowatts of heat transfer. The first heat exchanger ends up with an area of 9.24 meters squared, the second one 4.85 meters squared, the third one 9.16 meters squared. Together, this adds up to 23.25 meters squared. So the total area is 23.25 meters squared across 3 heat exchangers, compared with, well, by a remarkable coincidence, almost exactly the same, 23.15 meters squared, across 2 heat exchangers previously. So, we're going to have lower operating costs. We're going to need to make less use of hot and cold utility. Hot utility is the steam, cold utility is the cooling water, and these are things that we have to pay for. And so previously, we were going to have to supply 1,000 kilowatts of steam. Now we only have to supply 600 kilowatts. That's quite a substantial saving. Similarly, previously, we were going to need 800 kilowatts of cooling water utility. We've halved that down to 400 kilowatts. That's a significant saving as well. In order to achieve this, we're having to buy an extra heat exchanger. Our total area for heat transfer is much the same, by a coincidence, but it's now distributed across 3 heat exchangers. That's going to be a bit more expensive. So we're spending more on capital cost to buy our heat exchangers in order to have reduced operating costs in terms of the energy associated with steam and with cooling water. Now, this is interesting. We've got much the same heat transfer area, even though our temperature driving forces are now quite a lot smaller than they were. And we know that if the temperature driving forces are smaller, then the heat exchangers would need to be bigger. If from Q equals UA delta T, if you've got a smaller temperature driving force, then for the same amount of heat transfer, you need bigger heat exchangers to achieve that. But of course, we haven't got the same amount of heat transfer. Previously, we were doing a total of 1800 kilowatts of heat transfer. We're now doing 400 plus 400 plus 600, which is 1400 kilowatts. We're actually doing less heat exchange because we're no longer transferring heat or providing heat or taking away heat unnecessarily. So we're doing less heat transfer altogether. We're not doing unnecessary heat transfer, and therefore our heat exchangers are smaller, but the temperature driving forces are also smaller, and so that has a compensating effect. And so in this case, our heat exchangers, the total area, turns out to be much the same. But as we've said, this total area is now distributed across 3 heat exchangers, and that's going to be more costly than 2 heat exchangers with that total area. Okay, so that's illustrated heat recovery and the amount of heat recovery that we could get and the benefits and consequences of doing so. How about recovering a bit more heat? Now, the theoretical limit of how much heat we could recover would be if we brought the hot stream all the way down to the cold stream inlet temperature of 80 degrees. Theoretically, that's as far as we could bring our hot stream down to 80 degrees using a cold stream at 80 degrees. Here it is. Let's move them together. The trouble is, this would give 640 kilowatts of heat recovery. So that's the maximum theoretical possible amount of heat recovery that we could achieve. The trouble is, of course, it would require an infinitely large heat exchanger, because by the time you get to the cold end, your temperature driving force has dropped to 0, and to get the heat transfer, you'd require an infinitely large heat exchanger. So that's not practical. A minimum temperature difference of 10 degrees C, that is a reasonable value that would be practical, that would lead to practically, realistically small heat exchangers. So let's move our cold stream back horizontally to the right a bit so that our smallest temperature difference is 10 degrees C. So here it goes. To achieve this, we need to shift our cold stream. Yes, how far do we need to shift it? We need to shift it so that its inlet temperature of 80 degrees corresponds to an outlet temperature of the hot stream of 90 degrees. So here it goes. Are you watching? There. Oh, that's not very far at all. Let's do that again in case you missed it. There we are. We've shifted our cold stream so that its inlet temperature of 80 degrees is now corresponding with our hot stream outlet temperature of 90 degrees C. Once again, dividing our system into the 3 heat exchangers, we can calculate the corresponding log mean temperature differences. We can calculate the areas of our 3 heat exchangers now. And now these areas are adding up to 32.33 meters squared. So now our heat exchangers are getting quite a lot bigger in order to get this additional heat recovery, which is 600 kilowatts of heat recovery. Having achieved 600 kilowatts of heat recovery using quite a large heat exchanger, look at that, 17.12 meters squared, we've now reduced our cooling water requirement all the way down to 200 kilowatts and our steam requirement down to 400 kilowatts. So, once again, we've got 3 heat exchangers. One of them is recovering 600 kilowatts of heat for free. This is free heat. This is heat that we're not having to pay for. We are paying for it by having to buy a large heat exchanger. But once we've made that investment, we're now getting that heat for free. So our operating costs have reduced. We've still got a heat exchanger using steam to provide the final heating of our cold stream. It's now using 400 kilowatts of steam compared with 1,000 kilowatts, if you remember, back at the beginning. So we've reduced our steam consumption by more than half. And steam is quite expensive, so that's a significant saving. Similarly, on our cold utility, if you remember, initially we would have required 800 kilowatts of cold water heat transfer, of cooling water. We've reduced that all the way down to just a quarter, just to 200 kilowatts. Cold utility isn't as expensive as steam, but even so, it costs us money, and we've reduced that cost down to a quarter. So that's a substantial saving. Notice now that the total amount of heat transfer that is occurring in our system is 1200 kilowatts. So once again, we're no longer exchanging heat unnecessarily. Our starting point was there was 1800 kilowatts of heat transfer that needed to occur. We've reduced the total amount of heat transfer to 1200 kilowatts because we're recovering 600 of that. The total area has gone up to 32.33 meters squared compared with 23.25 meters squared previously. So it's gone up by almost 50%, and we've got an additional heat exchanger in there as well compared with no heat recovery. The reason that it's gone up is because you'll see just by looking at the graphs, our temperature driving forces are a lot lower now because our curves are that much closer, our lines are that much closer to each other. This is offset to some extent by the fact that the total amount of heat transfer has been reduced. So that has a bit of a compensating effect. Even so, as a general principle, the more heat recovery you have, the larger the heat exchangers you need to achieve this. That tends to be the trade-off that you're balancing. So 600 kilowatts then represents the most heat that we can recover while maintaining a feasible minimum temperature driving force of 10 degrees Celsius. And this idea of the minimum temperature driving force is an important concept. So let's think about that for a moment. The minimum temperature driving force, it's so important that we give it its own little nomenclature, delta T min. And it determines the maximum possible amount of heat recovery. It determines the amount of overlap between our hot stream and our cold stream when we plot them together on the same temperature enthalpy graph, and hence the maximum possible amount of heat recovery. It also determines, as we've seen, the size of the heat exchangers and therefore the cost of the heat exchangers. So the optimum choice of delta T min depends on the balance between capital and energy costs. As energy costs increase, as they are doing these days, it makes economical sense to aim for more heat recovery, and so a smaller value of delta T min would be chosen. Okay, let's try to make this a bit more real by thinking what the heat exchanger network would actually look like for this system that we've put together. So here's our heat recovery heat exchanger. So this is our middle heat exchanger. It's got the cold water coming in at 80 degrees Celsius, and we remember our cold stream, not the cold water, sorry, our cold stream had a flowing heat capacity of 8 kilowatts per Kelvin. It's coming out at 155 degrees C, so that's a temperature rise now of 75, temperature change of 75 degrees C. 75 times 8 is 600. Yeah, 8 times 155 minus 80 equals 600 kilowatts, and there we go. That's the amount of heat transfer that's taking place in that heat recovery heat exchanger. Our hot stream is the other stream that's coming into that heat exchanger. It's coming in at 240 degrees C. It has a flowing heat capacity of 4 kilowatts per Kelvin. It comes out at 90 degrees C. So here the calculation is 4 times 240 minus 90. 240 minus 90 is 150. 150 times 4 is 600 again. Of course it is. 600. That's the amount of heat transfer that's going on in that heat exchanger. Our hot stream loses 600 kilowatts of heat. Our cold stream picks those 600 kilowatts of heat up. Fine, our hot stream, and we'll notice in passing our delta T min of 10 degrees Celsius. So our hot stream comes out at 90 degrees, our cold stream goes in at 80 degrees. The temperature difference at the cold end of the heat exchanger is 10 degrees Celsius. Our hot stream then goes through a further heat exchanger where it exchanges heat with cooling water in order to come out at 40 degrees. So here the calculation is flowing heat capacity of 4 times 90 minus 40, which is 50. 4 50s are 200 kilowatts. So 200 kilowatts of heat transfer takes place in that heat exchanger. Similarly, our cold stream now has to go through a further heat exchanger where it picks up heat from hot utility. It comes out at 205 degrees. That was its target temperature. The calculation here is 8 times 205 minus 155, which is 8 times 50, which is 400 kilowatts of heat in that heat exchanger. So there's our heat exchanger network showing all the temperatures in and out of the different heat exchangers and the amount of heat transfer that's occurring in each of them. Okay, let's see what would happen if we increased our delta T min to 20 degrees C. The cold stream inlet temperature is 80 degrees, so we now need to shift the cold stream until this inlet corresponds with the hot stream at 100 degrees C. So let's do that. There it goes. Right, so now we have a 20 degrees C difference in temperature at the cold end of the heat exchanger. Once again, dividing our system up into the 3 heat exchangers, we can work out that our hot stream is now losing a total of 560 kilowatts. It's cooling down from 240 down to 100 degrees, so a temperature change of 140. 140 times 4 is 560, so there's 560 kilowatts of heat recovery between our 2 streams. This means that the rest of the cooling of the hot stream will now require 240 kilowatts of cooling water. Similarly, our cold stream, the rest of the heating required to bring that up to its target temperature of 205 degrees C is now 440 kilowatts. So, we've got 40 kilowatts less heat recovery. When our delta T min was only 10 degrees, on the left here we had 600 kilowatts of heat recovery. Increasing the delta T min to 20 degrees has reduced our heat recovery to 560 kilowatts. So that's 40 kilowatts less. So we need 40 kilowatts more hot utility, and we need 40 kilowatts more cold utility. In other words, we pay for the lost heat recovery twice. It's a double whammy. So by avoiding the heat recovery that we could get with a delta T min of 10 degrees, we're getting less heat recovery. We're paying for that twice in terms of more hot utility and more cold utility. That's worth thinking about. And here's the heat exchanger network that we would get for a delta T min of 20 degrees, and you can do the calculations to work out, to satisfy yourself that those temperatures and rates of heat transfer all work out. The delta T min at the cold end of the heat exchanger is now 100 minus 80, which is 20 degrees, and it's left as an exercise to calculate the log mean temperature differences for each of the heat exchangers and hence the required areas. So, in summary, heat recovery saves energy costs by reducing the amount of both hot and cold utility required to heat and cool process streams. Heat recovery reduces temperature driving forces in heat exchangers, so it tends to increase the size and the capital cost of heat exchangers, but this is offset to some extent by the fact that less heat exchange is taking place because we're avoiding unnecessary heat transfer. So there's a bit of a balance, but in general, heat recovery reduces temperature driving forces, increases the size of heat exchangers, and can increase the number of heat exchangers that are required as well, which also increases the capital costs. So there's a trade-off between heat recovery, which saves you energy costs, and capital costs. The trade-off depends on the value of delta T min that is chosen. Now that was a simple system using just two streams, one hot stream and one cold stream, just to introduce and illustrate these principles. Of course, the scope for energy savings from heat recovery becomes even greater when there's lots of hot and cold streams and when these are considered together. And that will be the topic for a future talklet. Thank you. I hope you enjoyed that. I hope you found it stimulating and educational.